When you look at the walls around you or the roof over your head, you probably just see, well, color. But what if I told you that the ordinary paint coating our world is secretly a high-tech climate solution just waiting to happen? Today, we're looking at some totally groundbreaking material science that is completely reimagining what paint can actually do. We're talking about taking massive global waste problems and turning them into beautiful pigments, and engineering coatings that can literally air condition a building without using a single plug.
Okay, let's dive into this. 1.3 billion. That staggering number represents the tons of bio-waste generated globally every single year. And honestly, by 2025, that's expected to climb to 2.2 billion tons. It's just an astronomical amount of organic trash, stuff like agricultural runoff, garden waste, forestry byproducts. Right now, it often just sits there emitting greenhouse gases or polluting our waterways. But this exact problem sets the stakes for the first incredible innovation we're exploring today. Because what if this waste wasn't trash at all, but the raw material for an entire global industry?
Now, to understand why this is such a game changer, we have to look at the severe environmental costs of traditional paint. Standard commercial paints rely heavily on carbon-heavy oils, synthetic pigments, and toxic solvents that release harmful volatile organic compounds, or VOCs, right into the air we breathe. But then, on the flip side, we have the promise of truly sustainable paint. We're talking about entirely water-based formulations that actually utilize that bio-waste we just talked about, acting as carbon sinks, and incredibly, even providing passive cooling for our buildings.
Let's start with Section 1, Pigment from Waste, Sustainable Color. To get that sustainable color, researchers are actively turning a major waste problem into a beautiful solution. They've focused in on a very specific, everyday type of biomass, Syzygium cumini, which are commonly known as jamin leaves. By collecting these totally ordinary fallen leaves from garden waste and repurposing them, scientists are preventing waste accumulation in a big way. And even better, they're creating a circular economy biochar pigment. This completely bypasses the need for those oil-based commercial pigments that generate such heavy carbon footprints in the traditional paint industry.
The process of transforming a dead leaf into a high-grade pigment is actually fascinating. It uses a technique called carbonization. Step 1 is just collecting and drying the leafy biomass. But step 2 is where the magic really happens. The leaves are placed in a reactor and heated to 500 degrees Celsius for 4 hours. But here's the trick, it's done completely without oxygen. Because there's no air, the leaves don't burn to ash. Instead, they essentially bake into a stable, carbon-rich material, permanently trapping the carbon inside. Finally, this biochar is ground down and passed through a microscopic sieve to create an incredibly fine 0.21 micrometer pigment powder.
And this brilliantly illustrates just how successful the process is. This infrared analysis proves that the new biochar pigment has incredible color intensity and structural stability. The biochar holds its chemical properties perfectly over time. And honestly, the best part? It achieves this natural stability without needing a single chemical modification. It is literally just baked leaves and water.
Moving right along to Section 2, Zero Power Cooling, Radiative Cooling.
So we've solved the pigment problem, right? Let's pivot to reinventing the rest of the paint so it acts as a zero electricity air conditioner. The key here is passive radiative cooling, or PRC. The definition sounds complex, but it's actually beautifully simple. PRC materials are engineered to do two things at the exact same time. First, they act like a mirror to the sun, minimizing the solar energy they absorb. Second, they act as a thermal exhaust, maximizing the heat they emit in the mid-infrared region. Because the Earth's atmosphere happens to be highly transparent to these specific infrared wavelengths, the heat doesn't just bounce around the air, it escapes directly into the freezing cold sink of outer space. And it does all of this without using a single watt of power.
Now, what's really interesting about this slide is how it visualizes the process in action on a scorching sunny day. If you follow the arrows here, you see the paint immediately scattering the sun's harsh visible and ultraviolet rays away from the building. At the exact same time, those other arrows show it emitting infrared heat from inside the building directly out into the atmosphere. The result? The indoor temperature actively drops while the outdoor surface bakes.
To pull off this effect without resorting to a bunch of toxic chemicals, researchers formulated a completely new type of paint using calcium pyrophosphate, or CPP.
Now, CPP is a natural biomaterial. It gets mixed into an eco-friendly, fully water-based acrylic binder. They completely eliminated the hazardous formaldehydes and volatile organic compounds that are usually required to make high-performance cooling paints. So it's safe, it's natural, and it's scalable. But how well does it actually work? 98%. Just let that sink in. That is an astonishing number. This specific water-based CPP paint reflects 98% of incident solar irradiation. That practically means almost none of the sun's heat is making it through to your roof.
Which brings us to the obvious question of how. Section 3. Particle size secret, broadband scattering.
So the crucial point is why exactly this specific paint reflects so much more sunlight than traditional materials. When we look under the microscope, we find the answer. In the standard paint industry, the absolute go-to white pigment is titanium dioxide. It's heavily processed to have neat, highly uniform particle sizes of exactly 300 nanometers. It looks perfect, but it's actually deeply flawed for this use case, because sunlight contains many different wavelengths. Look at the CPP particles instead. They are messy and highly dispersed. They range anywhere from a few hundred nanometers all the way up to large 5-micron chunks. This chaotic, varied size distribution is the exact secret to broadband scattering. The small particles bounce back the short UV wavelengths, and the large particles scatter the longer near-infrared wavelengths. It's like a giant puzzle where every piece blocks a different type of heat.
The result of that messy particle distribution gives us a massive performance leap. As you can see, while industry-standard titanium dioxide taps out at about 92% solar reflectance and calcium carbonate hits 94%, our eco-friendly CCP easily beats them all. By utilizing the broadband scattering power of its varied particle sizes, it reaches that near-ideal 98% reflection.
But lab tests are one thing. Section 4. Built for reality. Durability testing.
Because let's face it, lab science only matters if it can survive the brutal reality of actual weather and construction. To prove its viability, researchers put this paint through some extreme environmental testing. They literally submerged it and spun it in water at 350 RPM for a full hour just to simulate intense driving rain. Then, they blasted the exact same sample with intense UV radiation at 5 milliwatts per square centimeter for 5 straight days to mimic years of harsh sunlight. The result? Absolutely zero degradation. The paint didn't wash away, it didn't yellow, and it didn't lose a fraction of its optical performance.
Let's move to and see how this builds when we introduce mechanical stress. Because roofs expand, contract, and get walked on all the time. When subjected to 50 cycles of severe 90-degree bending, the CPP paint showed zero cracking. They also ran a really rigorous tape adhesion test to ensure it bonded aggressively to surfaces without leaving any residue. They even put it through 1,500 cycles of mechanical abrasion, proving its wear resistance is totally comparable to heavy-duty commercial latex paints.
So looking across this entire gauntlet of tests summarized here, the takeaway is pretty profound. By switching to this eco-friendly, water-based biomaterial solution, you sacrifice absolutely nothing in commercial-grade durability. This stuff is ready for the real world. Section 5. Sustainable Future, a Global Impact.
Let's zoom out now and combine these two converging paths. We've seen how we can take a massive global liability, 1.3 billion tons of biowaste, and transform it into incredibly stable, valuable biochar pigment just by baking it without oxygen. We've also seen how utilizing the chaotic, messy particle sizes of natural calcium pyrophosphate allows us to passively cool our building infrastructure without using a drop of electricity. And we've learned we can do all of this using water-based binders that completely replace toxic VOCs, all while rivaling the durability of traditional earth-harming commercial paints. Together, combining these innovations paints a vivid picture of a radically sustainable future.
Which leaves us with this final thought. Paint is one of the oldest, most ubiquitous, and frankly seemingly mundane human inventions out there. Yet, as we just saw, it holds the potential to be a highly advanced tool for cooling our cities and sequestering our carbon. So if we can completely reinvent something as simple as the paint on our walls, what else around you can we redesign to save the planet? Keep learning, keep questioning, and thanks so much for joining me for this explainer.